Continue our discussion of elementary matrices. In particular, I want to start by proving that an elementary row operation on vectors or matrices is equivalent to multiplying on the left by the corresponding elementary matrix obtained by applying the row operation on the multiplicative identity of the appropriate dimension. Here I'm going to call R any elementary row operation. R would map Rm into Rm. It should be clear that any elementary row operation on vectors in Rm is actually a linear transformation. These two basic properties are always going to be satisfied. I will leave this as an exercise for you. But the important point is every elementary row operation is a linear transformation. And we already know every linear transformation mapping Rm into Rm can be represented by a matrix product on the left. So this follows that the elementary row operation R acting on U should be equal to E times U, where E is some m by m matrix. But the question is, what is the matrix E corresponding to that elementary row operation? Let's let I sub m be the m by m multiplicative identity. Then the following should be clear. I sub m times u should equal u for any m vector u, and R acting on u, or R of u, equals E times u, which is E times I sub m times u, which by associativity of multiplication of matrices is E im times u, which is equal to R acting on the columns of I, in other words, R of I sub m, times u. Since this holds for all u, this actually means that E is the elementary row operation acting on the matrix I. The matrix E associated with the elementary row operation is the row operation applied to the multiplicative identity of appropriate dimensions. Let's talk about multiplicative inverses now. There's some new language that we use for invertible matrices. This will be more in the future. Non-singular. A matrix is non-singular if it's invertible. But for now, I will return to our language of invertibility. A square matrix, m by m matrix, is invertible if and only if there exists a matrix B of the same dimensions such that AB equals BA equals I sub m. We usually designate this matrix B by I superscript -1. It looks like a to the -1 power. I should say a to the -1. All right, you're familiar with that. Every matrix vector equation of this form, A times an unknown vector x equals a known vector B, will have a unique solution, x equals A inverse B. This is obtained by just using this equation directly above and multiplying on the left by A inverse on both sides and simplifying. I will leave that as an exercise for you as well. Now, you're always going to have unique solutions in a case like this if and only if the rank of A is actually equal to m. Remember, m is an m by m matrix. This is equivalent in turn to saying the reduced row echelon form of A is equal to the m by m multiplicative identity. Thus, if A is an invertible matrix, then there is a finite sequence of elementary row operations on that matrix A that finally terminates with the identity. This means that there is a sequence of elementary m by m matrices, E1 through EK, such that if I multiply it consecutively by those matrices on the left, such as you see here, I will finally end up with I. The note about invertibility, remember from the previous video we showed that every elementary matrix is in fact invertible. From this equation right here, it follows that EK multiplied through to E1 in the appropriate order is actually A inverse, and that A itself can be written this way: E1 inverse, E2 inverse, all the way down to E sub K inverse. Now, notice by forming these two products, A inverse, and A inverse A, you will get I in both cases. This shows that although matrix multiplication is not generally commutative, in this case it necessarily follows that A and A inverse commute multiplicatively. Now we can take all the information that we gathered above here and finally draw this conclusion. Every invertible matrix is the product of elementary matrices, and conversely.